familiar with function notation, we kind of want to make sure we've got, some good solid comfort with it. So let's say we've got this quadratic here. We call this a quadratic because it's a second degree polynomial. It's got that x squared. And we can certainly evaluate this function at different places. We could say find f at -5. Oh, do make sure while you're doing all this, you've got some paper with you and some pencils. I am going to stop periodically and ask you guys to do things. So, and it's really important, again, probably more important in this situation to, have you guys be doing those things and writing those things out. You're not going to be able to necessarily share it with me as much as might be nice, but doing those hand tools and not being as passive as might be tempting during our times is going to be real helpful. So we could find f of -5, and we could find f at, say, we could even find f at, say, x plus 3. That might be fun. We could find f at, let's take a moment and do these. So f at -5, well, let's actually do one nice, real simple one together. Let's say we wanted to find f at 2. We know what we would do with that 2. This says, hey, go find the function f. This is the function f. And where its independent variable is, the independent variable is denoted in those parentheses after the f. So let the independent variable equal 2. So wherever we see that independent variable, we're going to put the 2. So 3 times the 2 squared minus the 2 plus 1. Now, it's not vital, but notice I did put, like, these parentheses here are important. These parentheses here aren't necessary, but it's a good habit whenever you have something you're substituting into a variable to remember that, everything that's happening to that variable is happening to that value or expression that you're putting in. So I really like the habit of putting these parentheses around anything I substitute in. Even if they don't end up doing much, they remind me to do things like distribute when I have to, or be careful with the order, make sure this doesn't become a 6 before this becomes a 4. So being in that habit of putting those parentheses there can be really helpful. So then this is going to become, 3 times 4 minus 2 plus 1, or 12 minus 1, so a nice 11. So f of 2 is 11. So we can presumably do that with all of these. Take a moment. I'll give you 2 or 3 minutes and write out what f of -5 is. These might be a little tougher, but that's good. That's what I want to look at. So then write out f of x plus 3 and f of 2 minus x. Take a moment and do that. And if you have any questions, let me know. I'll kind of follow along here. The usefulness of those parentheses is probably a little more apparent in this problem than it was in this one. So just to make sure we're all on the same page, I'll give you a fair amount more time for the expressions. Justin got 81, great. Evaluating functions at these expressions can take a little bit more and can often feel a little bit weird, particularly with the variable, the x in this expression. But the rules are essentially the same. When we evaluated this f at -5, we took that -5 and put it in for those x's. So that's our general tool. Same thing here. That 2 went in and became those x values. So here we're being told a similar thing. Take the function f, and where its independent variable is, put x plus 3. So that expression, x plus 3, is going to go in for those x's. So f at x plus 3 is going to become 3 times that argument. So 3 times x plus 3 squared minus that argument, because that's where our x's are. So it's going to become x plus 3, and then plus the 1. So that's still 3 times the value of our independent variable squared minus the value of our independent variable plus 1. With the same function, we're just putting kind of another, not truly another function really, but another expression into that function. If you remember function composition, we're essentially doing that here, doing function composition. Before we evaluate this out, any questions about that? You guys happy about that? Some thumbs up. Awesome. So we do have to remember some of our tools here. This is usually the important part. Remember, we're squaring a binomial here. There's certainly a temptation to have this turn into x squared plus 9. But remember, of course, we can't do that. We do have to take the x plus 3, multiply it by x plus 3. So if you want, we could go over here, take x plus 3, multiply it by x plus 3, and formally FOIL it out if we need to. We'd have x squared, you'd have 3x plus another 3x plus 9. So you'd end up with x squared plus 6x plus 9. So we do have to remember that middle term that's going to be created when we square binomials. We're going to be doing a lot with square binomials, with little perfect squares. So this pattern is going to be a really good one to make sure you're familiar with. Oftentimes, when we look at perfect squares, we'll do them, or want to do them anyway, quite a bit faster. So the kind of pattern that we have here, the fact that we end up with the square of this first term, and then this 6 is twice the product between the 3x, or the 3 and the x, so we get 3x, twice that is 6x. So here we'd have negative 5x, twice that would be negative 10x. So the square of the first, twice the product, and then the square of that last term, plus 25. So that square of the first, twice the product, square of the last, you've probably seen that pattern before. but it's going to be an important tool as we go along, not only because we're going to be using a lot of perfect squares, but we're going to be wanting to build squares, and this is what squares look like. But for now, we're going to take that x squared plus 6x plus 9 and put it back into here. So 3 times this x squared, or sorry, this x plus 3 quantity squared becomes x squared plus 6x plus 9 minus x minus 3. Make sure we distribute that negative. That's what the parentheses help us remember. Plus 1. And then 3x squared plus 18x plus 27. Minus x minus 3 plus 1. Oh, it's weird down there. And then, what, 3x squared plus 17x. And then plus 25. Does that look right? Anybody want to back me up on that? Justin, I know that's a little bit different than what you had. Did you have something different when you multiplied out this, or? I would think this distribution. But anybody else end up with that result?
Yeah, I got this. I got it slightly different because I wasn't sure if I had to distribute the -1 across the x plus 3.
Here, yeah. And again, that's what those parentheses help us do. Like even here with this -5, the parentheses help remember how that negative is going to interact. But here, that distribution, yeah, becomes fairly vital.
I forgot to distribute the negative.
Somebody asked me once, how long does it take until just negative signs stop being a problem? And I always tell them, when it happens to me, when I stop making mistakes with negative signs, I'll let you know. So little negative errors are a common issue. Probably the best thing to do is good notation will help keep your negative signs in check more than most things. So, Crystal, what about you? Did that work out? Cool. Zoe, James, Ava, and Aaron, I can't see you guys, so I hope you have happy, smiling faces. That was terrible. So try to do it with this 2 minus x if you haven't played with that already, and we'll look at that together in a minute. By the way, do let me know or stop me if I, make any weird errors, particularly in this format. I think that's going to be a little bit easier, but it happens to me anyway. If I happen to do something like take 27 minus 3 plus 1 and get 85, stop me and tell me. So do kind of, it is helpful to have you guys stop me and correct me as I go along. Oh, good, Justin. It worked out when you distributed, right? Good. Okay. Let's look at that. And if you ever want more time to play with these things, without being able to quite see everybody as nicely, it's hard for me to tell where you guys are in your processes. So if you ever want me to give you a little bit more time with something, just say, hey, I have a little more time. Usually happy to. So we still have that 3 times stuff squared minus stuff plus 1. This is, essentially what our function looks like. We just use x's instead of these big spaces. And whatever's in here is going to be what fills those boxes. So that's going to become our 2 minus x and our 2 minus x. We've got to make sure we FOIL this out correctly and distribute the 3 correctly. And as you guys have noticed, being careful with that negative sign. So 3 times, again, I'm going to use that pattern, square the first, twice the product, so 4x, and then the square of the last, so plus x squared. If it helps to write out the foiling, do it. Go off to the side, FOIL that out, put it back there. Good notation will take us a long way. But I do want to recommend that you guys get comfortable with that pattern, that square of the first, twice the product, square of the last. It's going to come up quite strongly later. Distributing that 3, 12 minus 12x plus 3x squared minus, I'm going to combine these if that's okay, to a minus 1 plus x. And I'm going to reorder these a little bit. 3x squared, that would be minus 11x minus 11. Justin, you got a negative 13x. Did this negative distribute? Negative signs, am I right?
I just wrote it down incorrectly.
That happens too. Questions about any of those? And again, as I said, we might be a little bit rusty depending on how long it's been. Every once in a while, I've got somebody who their last math class was 20 years ago, and that can take a little while to get back in the swing of things. So questions about any of these before we start kind of messing with this? I'm going to have to get used to all the quiet. It's like, is it a problem or is it just revealing my own insecurities? I don't know. It's hard to say. So there are lots of different types of functions. We will be dealing with, figure out a way to make that eraser faster. We'll be dealing with several of the major classifications of functions. The main ones we're going to look at are first linear functions, lines. So we've all had some experience with lines. We will look at quadratics. And as you've got some experience with quadratics, graph as nice little parabolas. We'll then deal with larger degree polynomials. Larger degree polynomials essentially look like quadratics. They just, keep wiggling and keep bending depending on what's going on with them. We'll take a short dip into rational functions. And we'll talk a little bit about why they're called rational functions when we get there. Rational functions are interesting. They often have vertical asymptotes and horizontal asymptotes. They've often even got holes in them. So rational functions usually start to behave in kind of interesting ways. And because of the rationality of them, because they bring in dividing, they often have issues caused by division, like holes and asymptotes and gaps and stuff. Then we will go play with exponential functions for a little while. Exponential functions you're hearing a lot about now with things like spread and growth of viruses. So keep an eye out on that. So we'll talk about exponential. This is exponential growth, exponential decay goes the other way, but we'll talk about exponential functions. We'll spend a fair amount of time talking about logarithms and their connection to exponential functions. Look at their graphs. And at the very end, we'll actually take a little bit of a break from functions and talk about conic sections. Conic sections, some of them are, or some of them can be functions, but they are things like circles and ellipses and hyperbolas. But they're also parabolas, so parabolas can be functions, but sometimes parabolas go that way, in which case they're not functions because they won't pass that vertical line test. Most of these don't pass that vertical line test, except some of the parabolas. So we'll spend a little bit of time talking about circles, ellipses, hyperbolas, and parabolas in a more general way near the end. Oh, also, depending on our time in between here, we will talk about systems of functions. So that will be using, these basic types of functions, but putting them together into systems and finding where they match up. So our system might include linear and quadratic functions, in which case we can find intersections and plot them and do all kinds of fun stuff with them. So this is kind of the map for what we're going to look through in this course. Again, some of these will be more familiar and things you're more used to. Lines and quadratics, you've certainly got a fair amount of experience with. Polynomials, you've got some experience with. Rational functions might be new. Exponents and logs will be expanding on what you know before. Some of the conic stuff you may have never seen before. But our goal is going to be to expand and strengthen these skills and kind of get them to be working together. By the time we get into our section on systems, we're kind of using many of these, if not all of them, together. So that should be fun. When we back up a bit and talk about linear functions, when we talk about lines, one of the things that makes lines nice is the fact that they behave in a very stable way. What makes them a nice straight line is the fact that they've got that constant rate of growth. As we go along in our X, we change in our Y in a very stable fashion. We could be increasing, as this first one is. We could be decreasing, as this second line is. But the amount at which we decrease, the speed at which we increase, is constant throughout a line. It's what makes a line a line. The property, one of the things we call that rate of change, there's a nice word for that rate of change, nice word for that increasing and decreasingness that we have here. Do you guys remember what that's, or what some of the things we call that is?
Growth.
Aaron, I got slope. Somebody said growth. It can be either growth or decay. But I like Aaron's slope. Slope is kind of the generic term in a line for the rate of change of that line. We'll talk some more about slope for lines specifically when we get into chapter 2, but that idea of slope being the change in Y in ratio to the change in X is a common way for us to express this rate of change. If you haven't used it or seen it before, this triangle is actually the Greek uppercase it's not coming out. The uppercase delta, so delta y over delta x. We use delta often for change in. So this really just says the change in y over the change in x. That's how we calculate our slopes. Usually we see it written as a y2 minus y1. How do we find the change in something? Well, we find the difference, we subtract them. So we're probably more used to seeing slope written that way. Uh, but those are equivalent notations, or they mean the same thing. And you'll start seeing this notation more often. Your calculator actually uses it in a couple of spots. So ideally, we're fairly familiar with the idea of slope. The trouble with slope, and the trouble with rates of change in general, is if we move on to something even as simple as a quadratic. That was terrible. Getting used to trying to write with this thing. So if we move on to something as simple as a nice quadratic, the idea of this quadratic having a slope, a rate of change, falls away fairly quickly. Its amount of change varies throughout its domain. So the domain is the set of inputs, range the set of outputs. So as we go through this, the x values that are going into this, how much the y changes varies as we go through that domain. Here the function is decreasing as the x increases. So we're decreasing until we get to this x value, and then after that we're increasing. So we go from a negative rate of change to a positive rate of change. Let's say this value was an x of 2, so we'd be decreasing on the interval from negative infinity to 2, and we'd be increasing on the interval from 2 to infinity. So without that nice constant rate of change, we have, in some ways, unfortunately, we have a more complicated situation here, but also we need that because a lot of things don't have a constant rate of change. You toss a ball up in the air, its speed is not the same, its change in position isn't the same all the time. If the only thing we had to model things was lines, we wouldn't be able to model a lot. So we need this, these functions that vary in how much change they have, but also being able to express, hey, how fast is this thing changing? What is this thing's rate of change is really helpful. So for something like a parabola, we can't say what its singular rate of change is, but what we can do is try to find what we call an average rate of change. Now, average rate of change is still going to be slope, essentially, but how much this thing is changing, since it depends on where we are along the curve, we're going to be finding an average rate of change on some interval from A to B. So let's say we had a function here. Oh, let's say it's, what do I want? I'm going to build this real quick, just to throw in some notes here. If I want that intercept at 1 and that intercept at 3, then x minus 1 is going to give me an intercept at 1. X minus 3 is going to give me an intercept at 3. So if we multiply those together, x squared minus 4x plus 3 would be a parabola that has those two intersections. So then you erase that so nobody knows how you did it, and you look really smart. It's always a trick. So let's say we had this parabola and somebody wanted to know what is the average rate of change on the interval. Oh, let's say we go from 2 to 5. It should be fairly clear that from 2 to 5, this function is increasing as we go from 2 to 5. It's increasing. At first, it's growing fairly slowly. By the time we get near 4 and 5, it's growing pretty fast. So that average rate of change, well, it's going to be affected by these small values and these high values. Why did I do the x minus 1, x plus 3? I just wanted to be able to make a function that looked like this graph. We'll talk more about it when we get into our section on polynomials. But if I wanted to have x equal, let me do it that way. If I wanted x equal to 1 when y was equal to 0, that's this point at 0, 1. Sorry, not at 0, 1. This point at 1, 0. That means my function f at 0. Yeah, got thrown off there. Sorry, getting distracted by my tools. That f at 1 has to equal 0. If I want to have this intercept, this point at 1, 0, I need the function to equal 0 when x is 1. So if the function equals 0 when x is 1, x minus 1 will equal 0 when x is 1. So if a function has this as a factor, it's going to have that as an x-intercept. Similarly, x minus 3, if we plug in this 3 minus 3 is 0. So at positive 3, this factor is going to equal 0. So this whole thing will equal 0. So trying to build a polynomial when we know it's x-intercepts, its zeros, can be really helpful. And that's why the minus is, because we need this subtraction to equal 0. We need that subtraction to equal 0. Cool. So if we want to find, we can't find a rate of change between those 2 points because it's changing all the time. There isn't a single value for it. But if we want to find an average, we could presumably find little tiny slopes of little tiny lines in between those two, add them all up, divide by how many there are. But the easier thing to do by far is to consider the line between those 2 points. That line is technically referred to as a secant line. Secant from the Latin to cut. It cuts through the function. I'll leave it in that color. So if we want to find an average for the rate of change here, that secant line is good at doing that. Because notice if we looked at, say, the slope of this part of the function, that's much steeper than that purple secant line. If you looked at slopes down here, they're much shallower. So ideally, it should be believable that this slope is an average of all the little slopes we could build along that way. If we wanted to prove that, you'll prove it really early on in calculus. Calculus 1, by the way, is all about slopes. So this will be a big part of your Calc 1. But just if we want to find the slope of this secant line, that slope of that secant line will give us this average rate of change. So if we want an average rate of change, we are really just finding a slope. Well, how do we find a slope? We've got a tool here for finding slopes, right? Change in y's and change in x's. Unfortunately, all we have are the x values. Our x values go from 2 to 5. We need to find the y values that associate with these points so we can find the change in those y's. Well, luckily, down here, we have our function. How do we turn these x values into y values? That's what this function is supposed to do. So if we wanted to know the y value down here and the y value x up there, if we take that function f and plug in the 5, f of 5, That's going to give us the y value when x is 5, minus f at 2. That's going to give us the y value when x is 2, over the 5 minus 2. That's the 5 minus 2, that change in x. This formula, this average rate of change formula, f at 5 minus f of 2 over 5 minus 2, specific to those points. But this formula should look exactly the same as that slope formula. And of course, it should look like it's the same because it is. This is exactly the form for a slope of a line. It's just in function notation instead. F of x2 minus f of x1. That's our change in y over x2 minus x1. That's our change in x. This is still change in y over change in x. It's just slope. It's just in function notation because we need to get the y values from our function. So I'll give you a minute or two. Find those. Find f at 5 using this function f. Find f at 2. Find their difference. Divide by the 5 minus 2 to find the slope of this purple secant line, or pink, or fuchsia, whatever color it is. I'll give you a couple minutes to do that. Well, that worked out to be a nice clean number. Questions about it? Any of that? Just went off to the side here to evaluate those. Plug those back in. We do have to be careful here with that minus the -1. But that 8 minus -1 does give us a nice 9. And this ended up being a nice whole number. That's kind of fun. Doesn't happen all that often. But what does this 3 represent? Let's say this x was, I don't know, feet. And this y was in, I don't know, Eggs. I don't know. Why eggs? No idea. So what did we do here in terms of our eggs and feet? These, this function is taking in a number of feet and outputting an amount of eggs. So at, 5 feet, we got 8 eggs. Why are we getting eggs per feet? I have no idea, but it's not important. At 2 feet, we got -1 egg. So at 2 feet, we lost an egg. Okay, fine. What does that mean? Well, when we're finding this average rate of change, these function values are numbers of eggs, and these x values are numbers of feet. So what is this 3? This average rate of change, this 3 is 3 eggs per feet. It's 3 y's per x. Is, remember, change in y, change in the function over the change in x. So change in the function over change in the inputs. So if our output is eggs and our input is feet, this 3 is eggs per feet. So what is our rate of change between 2 feet and 5 feet? Our average rate of change between 2 feet and 5 feet is 3 eggs per foot. We're not always making 3 eggs per foot. Here we're making less, here we're making more, but on average between those two, that's our rate of change. So often when we're dealing with rate of change, you'll be asked to not only find the value, the 3, but interpret it. And generally that interpretation involves the units. What does this mean? Eggs and feet might be a little silly, but they really can be anything. If this was, say, I don't know, bananas, and this was puppies, what's this 3 represent? Well, that 3 would be between 2 bananas and 5 bananas, we are increasing at 3 puppies per banana. I have no idea what that means. But it doesn't matter. If those are the units, that's what this function is saying. Fair? All right. Let's see, I've got 2 minutes. So we'll need to talk about the difference quotient tomorrow. So be prepared for that. Average rate of change is one of our big tools. But another version of this average rate of change takes this and puts it in slightly different terms to give us a tool that you're going to use later on. So tomorrow, what's tomorrow? Wednesday? So tomorrow we will start with our discussion on the difference quotient. But just to break that down, the difference quotient, difference should be subtraction, quotient should be a division, right? So our difference quotient will be a division of subtractions. Well, that's what this is anyway, right? This is a quotient of differences. So really our difference quotient, we're still going to be talking about slope, just in a particular way that's going to set us up what you're going to have to do in calculus. So that's where we're going to leave you today. Do please make sure you are reading, let's see, 1.3 if you haven't already, and 1.4. 1.4 will have this difference quotient in it. And make sure you look at those. My Open Math, you've got some that are due. Oh, I just checked. When are those due? I think they're due Thursday. They might be due Wednesday. Do them by Wednesday anyway. My Open Math, you've got 2 assignments due this week. But also start working on that 1.3 and 1.4 on My Open Math. Don't fall behind. Stay as far ahead as you can. It's going to pay off as we go along. Before I let you go, do you have any questions? Anything I can help you with?
I do. I haven't really investigated, but I have written down the things we have to do this week. And for the hand-in and the discussion, Is that something we can start working on now, or should we wait for instruction to do that?
The hand in, I would wait for a bit. I have that on my notes for talking about tomorrow.
Okay.
In terms of the discussion, the ideally you've already looked at doing the introduction.
Correct.
The discussions for each particular week are asking you guys to talk about, what was a difficult problem or the problems that you had during that week or things that you're working on that week. So while I'd like you guys to do those earlier rather than later, we do have to get into the week some a bit before you guys can be talking about that.
Okay.
So really, as soon as you start hitting problems that give you any trouble or you want to discuss, start throwing those on the board. And of course, always, if you run into a problem early on the week and you want to post about that, great, do it. If you run into another nasty one later in the week, post that too. The more we can communicate with those boards, the more we can get out of them. Okay, well, have a wonderful day. Everybody stay safe out there. And as always, if you need anything, let me know.